Thank you very much. For the last half hour or so, we've been watching this cloud chamber to see cosmic rays coming through the building. But now we're just going to switch to the normal part of this talk, if you want to call it that, and I'll be switching back to demonstrations that are running on this front bench as time goes by. So, what are we talking about this evening? We're going to be looking at radiation of one kind or another. I'll start by looking at background radiation, terrestrial radiation, before moving on to cosmic rays, thinking about the history of how they were discovered, how we knew cosmic rays existed, and then looking at how cosmic rays can be detected here on Earth, and where are they coming from? These charged particles that seem to be screaming across the universe, where did they come from in the first place before they arrived here on Earth? And then at the very end, I will summarize. Firstly, the Liverpool LiAS insist that I tell you that I have some radioactive samples on the front bench here. There is no hazard to you. I will put them away after I've used them, such that if you want to approach the bench and take a closer look at the cloud chamber, it'll be perfectly safe for you to do so. Okay? So on this bench, there are a couple of types of detectors, which I'm going to come to in due course. There's a Geiger-Müller detector, the yellow box, and there is a cloud chamber. Both of these are going to be used at different points in the talk here. So firstly, can you hear the clicking? Okay. Each click signifies the arrival of a subatomic particle coming through the detector. I'll explain later how the detector works. So this particular detector is normally called a Geiger counter. It should be called a Geiger-Müller detector. That's what physicists insist that it's called, but everybody calls it a Geiger counter, so we're going to stick to the vernacular. But each click signals the arrival of a particle coming through the detector. Maybe that particle came from an atom looking somewhere in this room, but maybe that particle came from further afield. Maybe it came from a supernova in a galaxy far, far away, perhaps. It might even have come from a supermassive black hole. We'll see something about the origins in a little while. The bottom line is a Geiger counter doesn't tell you the origin. A Geiger counter just tells you something has passed through the detector. So let's have a think about background radiation before we move on to cosmic radiation to give us a little bit of context. So radiation is around you all of the time. It's not necessarily something to be worried about. It's something that we have lived with ever since the Earth was born. The Earth is radioactive. It's radioactive now. It was radioactive when it was made some 4.5 billion years ago. It's radioactive because some elements in the periodic table are unstable. They will decay into other elements. Let me just kill the Geiger counter for the time being. So when we look at all of the elements in the periodic table, which make up essentially all of the Earth and the solar system and everything else, we see some atoms that are stable. They've been the same way essentially forever. Once you've made the atom does not change. But there are some, the colored ones in the periodic table shown here, that are unstable. In other words, of their own volition, they will change into something else. They might start off as one element, but over a given period of time, they will change into a different element. And they'll do that by the nucleus emitting a subatomic particle. We can visualize that by moving across to either the Geiger counter or the cloud chamber. So let me start by switching to see some radioactivity. Now, it would be nice to actually show you the radioactivity of this piece of uranium. This is a piece of uranium glass impregnated with uranium, not because people want to have radioactive glass in their cabinets, but people put uranium in glass simply because it is nice to look at under UV light. It fluoresces like mad. That's just a side effect of having uranium in there. If we actually take this piece of uranium, and let me swing the camera around so you can see this, if I put it in front of the Geiger counter, you can perhaps hear that the rate is slightly higher, and you can perhaps see the needle move a little bit. It's not particularly radioactive, but it is unfortunately a bit too big to put into my cloud chamber, so I'm not going to use that. I'm just going to put that away, and I'm going to take a smaller piece of material that contains some uranium. This is safe in the sense that it's only small, and I bought it from a mineral supplier in America. It's only a few millimeters in size, but you can see if I hold it in front of the Geiger counter, it is quite definitely radioactive, even though it is absolutely tiny. So what we're going to do is to put that into the cloud chamber. Up till now, the cloud chamber has been showing us tracks from particles coming from the cosmos. Let me see if I can open up the cloud chamber, get the sample in and close it up again. I've now disturbed the cloud chamber, but you can now see quite clearly that there are tracks coming not at random in terms of their positions or their directions. They are quite definitely coming from the direction of the rock itself. Yeah? So in other words, this is one way of seeing radioactivity. Even if we didn't know it, we could tell that particular rock was radioactive from seeing the tracks coming out. Again, it may take a minute or so for the cloud chamber to settle back in, but we should be seeing lots of particles, lots of tracks coming out of a radioactive sample like this. If we watch it for a minute or two, can you tell that there are two types of tracks? Some of them are relatively narrow and quite bright. Some of them are a little bit broader and perhaps a little more ghostly, a little fainter. Exactly how well that shows up depends on how long the cloud chamber has been running. But there are definitely very narrow tracks every once in a while and more ghostly broad tracks showing up as well. So just in case, like a good scientist, I always have a backup plan. Just in case it didn't work too well, I had a little video of a mineral that I put into the cloud chamber quite some time ago. Again, let me get rid of the annoying clicking now. So here's a rather bigger crystal of uranium-containing mineral that I put into the cloud chamber some months ago and then videoed it. And again, you can see lots of particles coming off in different directions. Perhaps it's not so obvious in this video of which are the narrow ones, which are the more ghostly ones. But if I take a whole minute or two of video and add up all the frames, then it's a little easier to see what's going on. Can you now see that there are quite definitely relatively narrow, bright tracks in there and some rather large, broad, more ghostly tracks coming off in different directions? So simply by observing the different types of tracks, we get the impression that clearly something is coming out of this rock, and indeed any other radioactive rock that we put into a cloud chamber. But we can ask ourselves, what are they and why are there apparently two types? So we go back to a little bit of atomic physics. This is not an accurate indication of what an atom looks like, but it will do for the time being. An atom is a positively charged nucleus surrounded by a whole set of negatively charged electrons. The important thing is, although that's what an atom looks like, when an atom changes from one element to another element, what matters is what the nucleus is doing. It doesn't really matter what the other electrons are doing, it matters what that nucleus is doing. And don't worry about the detail in this cartoon, but this is just to show that it can get quite complex. If we imagine a heavy nucleus, like the nucleus of a big atom, like uranium, for instance, that uranium can decide to change into something else by the nucleus spitting out, well, it could spit out a proton. Alternatively, it could, in principle, spit out a neutron. Depending on what mood it's in, it might decide to spit out a couple of both, 2 protons and 2 neutrons at the same time. We call that an alpha particle because that particular particle is a very stable configuration of protons and neutrons. It also might spit out an electron, the electron that we know and love, which is negatively charged, but also there's a sort of electron, a cousin, if you like, to the electron, which is positively charged. It's an antimatter equivalent to the electron, and it's called a positron. Also, a nucleus might, in principle, spit out an electromagnetic ray such as a gamma ray. So there's lots of different ways nuclei can change by spitting out lots of different particles. We're not going to dwell too much on all of those, but I'll just briefly say something about the 3 most common types of radiation that you might have heard about. Alpha radiation, and in this particular talk, alpha rays and alpha particles are the same thing. In other words, when they were first discovered, we didn't actually know, are they a wave like a gamma ray, or are they a particle? And so sometimes they're called particles, sometimes they're called rays. It doesn't matter. They are the same thing. An alpha particle is the nucleus of a helium atom, and it's made up of 2 protons and 2 neutrons. And alpha particles do not travel very far through any medium. In fact, they cannot get through the glass of a cloud chamber. That's how I know that when we see an alpha, we know it didn't come from outside the cloud chamber. It must have come from radon gas inside, which I'll come to very shortly. Beta radiation, or beta rays, or beta particles, they are just electrons. Didn't know that when they were first found, which is why they were called beta. Not sure what they are. We now know they are electrons, but the old name still sticks. So beta rays or beta particles are electrons, and they are very lightweight. An electron is thousands of times lighter than an alpha particle. So an alpha particle is a bit of a bulldozer when it goes through materials. Electrons are much more light, and therefore they will rattle around and bounce off the atoms, for instance, that are inside a cloud chamber. A gamma ray is rather different because that is an electromagnetic wave. So it's not a particle in the same sense that an alpha or beta is a particle. Gamma rays are not charged, unlike alpha and beta, and therefore they will not leave tracks in a cloud chamber. So when we look in a cloud chamber at natural radiation, we will see alpha and beta particles. So if we switch back to the video camera, what we're looking at there, by looking at different types of particles coming out, different types of tracks coming out, we're looking at alphas and betas. Anything that's relatively narrow and relatively bright and relatively straight on this scale, that would be a beta particle. That's more than likely an electron. Anything which looks a little more ghostly and much broader, sometimes they're a little too broad to see very clearly, that would be an alpha particle. So now we understand what it is we're looking at, and a little later I want to see cosmic rays again, and if we leave a radioactive particle in, we can hardly see the cosmic rays because the radioactive mineral will be producing so many alphas and betas, it'll be difficult to see the cosmics. So I'll just take that out again, whoops, after dropping it. And it'll take a little while for the cloud chamber to stabilize again, but that doesn't matter because I'm going to be waffling for a minute or so about something else and then coming back to it. Okay, so we've now got an idea of what that is all about.
Steve, can I just ask you a quick question?
Yep.
When you run the video there,
Yep.
part of the rays emanating from
Yep.
the particle,
Yep.
there's also vertically from the top to the bottom, streaming. When you took that particle out, it was random.
The cloud forms by always falling. Therefore, as seen by the video, there will always be a top to bottom. So individual particles may appear to move at random, but as a whole, the entire cloud is always falling. So if we switch back to where we were, oops, switch back, sorry, to the... So again, this is just to remind us that that's what we saw before. The faint tracks are alphas, the bright narrow tracks are betas, and again, it shows up more clearly if you take a video and then add up all the frames of the video, then you can see more clearly that there are quite definitely some narrow tracks and quite definitely some broader tracks. That sort of helps you get your eye in when you're looking at cosmics a little later on. Now we need to say just a little bit for context again before we get on to cosmic rays proper, and that is that different atoms come in different types, so-called isotopes. They're sort of cousins of the same atom. And if we take a specific example, so we can see that a little more clearly, if we take carbon, for instance, you are made up of carbon, or at least a lot of you is carbon. Carbon has 6 protons in the nucleus because that's the definition of a carbon atom, is any atom with 6 protons is called a carbon atom. If a carbon atom has 6 neutrons as well as those 6 protons, it has a total of 12 protons and neutrons, and we call that carbon-12. You are made mainly of carbon-12, plus bits and pieces of other stuff as well. Carbon comes in a different so-called isotope. A cousin of carbon-12 is the same 6 protons, but if it comes in the flavor with 8 neutrons, then the total number of particles in the nucleus is 14, and we call that carbon-14. So you're mainly made of carbon-12, but a little bit of you is carbon-14. That's actually quite useful because carbon-12 is stable, which is just as well, but little bits of you are radioactive. You have a little bit of carbon-14 in you, that's radioactive, that decays, and that is how we do radiocarbon dating. That's how we know how old a tree is when it dies. We can use this carbon dating, look at the ratio of C12 and C14, and we can tell how long it's been since that object, that particular organic material, was alive. So carbon-14 is a very useful radioactive isotope, and it's in you now. Potassium is also radioactive, or at least certain isotopes of potassium are radioactive. If we know how much potassium is in your body, we can work out that in your body, approximately 4,000 atoms per second are decaying into something else. Now, that might sound frightening, that 4,000 of your potassium atoms are changing into something else every second and spitting out some radioactive material, but no, 4,000 per second is tiny compared to the number of atoms in your body, so that is nowhere near anything left to worry about. In fact, that is actually one of the largest contributions to background radiation. Thorium is another radioactive element, but it's actually more abundant than uranium, and uranium is probably more abundant than you think. You might think that uranium is a very rare material because you hardly ever see any around, lying around in the streets, but actually there's an awful lot of uranium in the Earth's crust. There is 500 times more uranium than gold in the Earth's crust. 3 parts per million. 3 parts per million doesn't sound much, but much less than that is dug out of the Earth because we value gold more than we value uranium. In the Earth's core itself, there's loads of radioactive elements, all of which are decaying and producing particles, which produces heat. So the core of the Earth has been kept warm or hot for billions of years because of radioactive decay of elements. That's kept the core hot, and it's kept the core molten. Because we have a molten core, we have a magnetic field. Take a molten metal core and spin it, you get a dynamo which generates a magnetic field. So the Earth has a magnetic field because of radioactive decay at its core. So it's a little bit ironic that radioactive decay produces a magnetic field which ultimately gives us a little bit protection against cosmic radiation. Mainly the softer stuff, the low energy stuff coming from the sun, but the Earth's magnetic field protects us to some extent, but that's generated itself by radiation. Another aside before we start to finish off this section, a little bit of potassium is a particular isotope called potassium-40. And potassium-40 is interesting because it emits beta plus. Beta meaning something that looks like an electron, but electrons are negatively charged, and what this particular isotope of potassium spits out is positively charged. So potassium-40 spits out antimatter. It spits out the anti-electron. And yet, of course, it doesn't do us any particular harm. And bear in mind that beta plus particles, antimatter effectively, there's lots of potassium not only in us, there's lots of potassium-rich foods, such as Brazil nuts, for instance, or bananas. For those of you who like bananas, bear in mind that there's enough potassium in there to spit out quite a few particles of antimatter. Not enough to cause you any harm. It's such a low dose, in fact, that somebody said, why don't we actually invent a new dose? Let's call it the banana equivalent dose of radiation. Rather than talk about REMS and RADs and sieverts and all of these other things that physicists talk about, let's have a radiation dose in banana equivalents, because then we can sort of relate to it. So some people have said, right, if eating one banana gives you a certain dose from the potassium in the banana, then for instance, at the moment, we know cosmic rays are coming through the roof because we've seen them in the cloud chamber. How many cosmic rays are going through you every day? What is your dose of cosmic rays that everybody is exposed to, no matter whether you're in the top floor, the ground floor, in a house? It doesn't really matter how thick the roof is. Everybody will be exposed to cosmic rays. And in terms of the banana equivalent dose, your dose of cosmic rays is roughly equivalent to 2 hands of bananas. So you would increase your dose by eating a banana every day. You would increase your dose a little bit, but obviously not by much. Bear in mind that it would be higher than that if you fly a lot, because we're talking about cosmic rays. The higher you go in the atmosphere, the more radiation you receive. So one final point before we move on from terrestrial radiation, And that is, not all radioactive elements come in solid form. It's not always something you dig out of the ground as a mineral, such as the mineral I showed you a little bit earlier. Radon, for instance, is not found in solid form. It's a radioactive gas. It's the result of radioactive decay of uranium that occurs naturally in a lot of rocks, in granite in particular. So whenever you have granite, you'll have some uranium. Wherever you have uranium, that will decay into radon. Radon is a gas. It'll bubble out of the rock and into either released into the air or possibly into your home or, in this case, into this particular room. Radon concentrations will vary across the UK simply because it's a question of how much granite is under your feet. Note that in Liverpool we have the lowest color, the lowest level of radon. It's not strictly zero, but it's relatively low because we have very little granite here. If we were to go down to Cornwall or Cambria or some of the highlands in Scotland, we'd find a lot more granite, a lot more radon, and we'd see far more alpha particles in our cloud chamber, especially in these areas of the UK. Radon gas emits alpha particles, and therefore, if we see alpha particles, remember, they can't travel very far through material, so they can't get into the cloud chamber. So if we see an alpha particle in the cloud chamber, it must be radon that's in there anyway. In other words, it's radon that's in this room and ends up inside the cloud chamber. So we've had our little aside to make sure that we all understand what we mean when we talk about cosmic rays and cosmic radiation. I thought I'd give you that little aside on terrestrial radiation to sort of set the scene. So where did the history of cosmic rays start? Well, if we look at the pioneers of radiation, I would imagine that most of you will recognize the person in the middle, Marie Curie. Some of you might recognize Henri Becquerel on the left-hand side, but I'm guessing that not many of you perhaps know Victor Hess. So Henri Becquerel basically discovered radioactivity. Marie Curie, some years later, synthesized and separated certain radioactive elements like radium and polonium, etc. The contribution from Hess I'll now describe. So back in the 1800s, in the late 1800s, it was known that you could charge a so-called electroscope. This is a way of measuring charge. An electroscope is basically two gold leaves sitting next to each other, and it's in a sort of a bell jar to try and stop drafts making a difference. Two gold leaves. If you charge them, positive charges on both leaves or negative charges on both leaves, like charges repel. So if you charge this up, the two leaves simply separate because they repel each other. But it was noted that whenever you charged one of these up by rubbing a balloon or a cat or a piece of amber or something and charging it up, it was noticed that these leaves would slowly collapse, indicating that they were discharging. So they figured something is discharging these electroscopes. There's some background radiation that's causing these things to lose their charge. Extra charge is getting in, either positive or negative, we don't know which. But was it coming from above or below? Was this mysterious background radiation coming from the rocks below our feet, or was it coming from the air? It was not known at the time. So Theodore Wolff, back in 1910, took an electroscope up to the top of the Eiffel Tower to see if he got any readings that were different from the bottom. In other words, you see how fast an electroscope leaf collapses to give you an indication of the strength of radiation. You do that at the bottom, and then you do it again at the top. Is there any difference? The answers were essentially inconclusive. You can't really tell over such a short distance. And then the question is, well, is there any possibility that actually the tower itself is radioactive? It's not a silly thing to think about. The tower's made of iron. Iron is dug out of the ground. If the ground is radioactive, maybe the Eiffel Tower is radioactive. Also, what about the atmosphere? We know radon exists, and radon exists in the atmosphere. How do you know whether or not radon is affecting your measurements? The bottom line is the height of the Eiffel Tower is not enough to distinguish between radiation levels at different heights. This is where Hess comes in and said, we need to sort this out. If we want to know whether background radiation is coming from below our feet or above our heads, we need something higher than the Eiffel Tower. A few hundred meters is not enough. So what do you do about that? He had the idea, you go up in a hot air balloon, and then you can go much higher than the Eiffel Tower. So in 1911, 1912, he took a modified electroscope up in a balloon to see whether or not radiation levels appear to change when you go away from the ground. If they go down, that implies that the radiation is coming from the ground. If they go up, it implies the radiation is coming from the sky or higher. So he did some balloon flights. In 1911, he went up to 1,000 meters, and the result was still inconclusive. Yeah, you get it changing a little bit, but the measurements weren't that accurate, so it wasn't clear what was going on. But he didn't give up. He said, if 1,000 meters isn't enough to tell you what's going off, let's go higher. And in 1912, he went up to 5,000 meters, and then he saw a dramatic increase in the levels of radiation discharging the electroscope. So effectively, as of 1912, he showed that whatever the background radiation was, it was principally coming from above, not below. There might be a small contribution from the ground, depending if you're standing on granite or not, but in general, this background radiation that they discovered in the late 1800s was coming from above. Okay, coming from above. Does that mean it's coming from the sun or somewhere else? How are you going to tell if it's coming from the sun or not? Well, one option, of course, is to take your hot air balloon flight and fly at night. Does anybody want to get into a hot air balloon, fly at night, get carried by the wind in a direction you can't see, and then land somewhere you can't see, I say land, crash somewhere you can't actually see what's going on? Nobody in their right mind would fly at night in a hot air balloon. So how can you tell if it's coming from the sun or not? Hess had the brilliant idea. You fly the hot air balloon on the day of a solar eclipse. Great idea. You make a measurement of the radiation levels, you wait for the eclipse, and you see if the radiation goes up or down or stays the same. During the eclipse, the radiation levels didn't change. Blocking the sun made no difference to the radiation levels, to the best of his ability to measure. So effectively, at that point, it was proved that this background radiation is cosmic. It's coming from above. It's not coming from the sun, or at least most of it isn't coming from the sun. Maybe the sun contributes a little bit, but not much. So this is when the idea of cosmic radiation was first born. And that's why Hess was awarded the Nobel Prize in 1936 for the discovery of cosmic radiation. So if you like, the birth of cosmic rays. We now have this sort of idea. This is an artist's impression of what's actually going on. It's not a very good artist's impression because, yes, it is indeed the case that a particle coming through space, hitting the top of the Earth's atmosphere, produces a shower, a cascade, an avalanche, if you like, of secondary particles. But this artist's impression implies that two showers can happen at once, and they both come from the same source, which is a bright star. That's not very accurate. So just ignore the bright thing at the top. But yes, a shower of particles, that we believe is what's actually happening. A single particle is coming in with some energy, hitting the top of the atmosphere, and that's producing an avalanche effect as it comes through the atmosphere. So this cartoon, if you like, on the right, shows you what we think is happening. A so-called primary cosmic ray, primary simply means outside the atmosphere. A primary cosmic ray is coming in, yet to be identified. When it hits an atom in the atmosphere, oxygen, nitrogen, whatever happens to be around, it produces a cascade of secondary particles. Each time new particles are generated, they share whatever energy of that incoming particle was. So in other words, if we measure the energy of all the particles down here and add them all up, we can work out what the energy of the incoming particle was. This is basically just an energy conservation sort of argument. The cascade of one primary doesn't necessarily produce half a dozen, as this cartoon. It's more like the previous slide. Actually, one incoming particle, if it carries enough energy, might produce thousands or millions of secondary particles as they come through the atmosphere. And these secondary particles are not simply the fragments of whatever atom they hit. If something comes into the Earth's atmosphere and hits an oxygen atom, it doesn't simply produce protons and electrons, the stuff that atoms are made of. Some particles are made in the process that do not exist in atoms. Some of these new particles are unstable and do not live more than a tiny fraction of a second. For instance, one of the most common to find at the Earth's surface is a so-called muon. These are generated by cosmic rays hitting the top of the atmosphere. A muon is not part of the atoms that make up you or me or anything else that we know about. They are different subatomic particles. They are similar to electrons, but much heavier. They are 200 times heavier than an electron, although they do share some other characteristics. Muons have no part to play in making atoms, and they only live for a tiny fraction of a second, something like 2 millionths of a second, 2 microseconds. That's how long a muon lives for. You might say that, well, actually, it hasn't got time to reach the surface. If it's being made tens of kilometers high, it shouldn't actually be able to travel that very far in 2 microseconds. But good old Einstein's time dilation means that it can actually arrive at the surface and be producing clicks in a Geiger counter or tracks in a cloud chamber. And there is proof, there is a muon. It's a collection of little droplets of alcohol in a cloud chamber. In this particular cloud chamber, this is one I photographed a few months back, and I've just changed the contrast a little bit to make it easier. So instead of having a grey background, it has a nice black background. But if it's a straight line, then that's characteristic of a muon. Muon is very energetic. Very little will stop it. Remember, it's come through the building. It comes through meters of concrete without even realizing it's there, goes through the cloud chamber, goes through the Earth, and eventually gets stopped in the Earth's crust a fraction of a second later. What about the primary particles? What are the particles that actually start this cascade? If what we see down here on Earth are electrons and muons and other particles, what actually started this process by hitting the top of our atmosphere? Well, so far we've been talking about the secondaries, but there's been enough research on the primary particles, mainly because we've now been able to go above the Earth's atmosphere with spacecraft and actually see what's hitting the top of the atmosphere. Research has told us that what's actually going on is that most of these cosmic rays hitting the Earth, 90% of them are protons. In other words, 90% of them are the nuclei of hydrogen atoms. A small number, only about 9% or so, are alpha particles. In other words, the nuclei of helium atoms, the next element up in the periodic table. And it looks like a rather tiny fraction are everything else. In other words, about 1%, whatever's left when you've taken 90% and 9% out. The remaining 1% are heavy nuclei of very heavy atoms. Which atoms? Well, basically the same sort of atoms that we see lying around the solar system. Here on Earth, we have 92 naturally occurring elements. It looks like the makeup of cosmic rays is roughly the same. Lots of hydrogen, a little bit of helium, a little less of every element all the way through the entire periodic table. So almost anything can hit us from above the Earth's atmosphere, though it's much more likely that we're going to get hit by protons than anything else. So how do we detect them? Either above the Earth's atmosphere, the primaries, or at the bottom of the Earth's atmosphere, the secondaries. Well, we've already seen one example, this Geiger-Müller tube, or Geiger counter, as we sometimes call it. What's actually going on inside that allows us to get click, click, click every once in a while? Well, basically, it's a cylinder with some gas in there, some inert gas, and if radiation comes in, it can ionize the gas, and because a voltage is applied between a central terminal and the outside casing of the cylinder, whenever you ionize the gas, plus goes one way, minus goes the other way, and a little box of tricks basically measures that ionization by effectively just measuring the current, because each atom that's ionized produces a very small current when it goes to the positive terminal or the negative terminal, and the current is simply converted by an amplifier into a click. So you can see that we can't really tell what the particle is. All we know is that something has arrived by the fact that we hear a click when the Geiger counter registers the fact that a particular atom has been ionized, or a collection of atoms have been ionized, and leads to a small current. What about the cloud chamber? Where did they start their lives? Well, Charles Wilson, back in, 1894, the story goes, that he saw the Brocken spectre on top of a mountain. He was looking at his shadow from the top of Ben Nevis, And around his shadow, he noticed some optical phenomena, some colored sort of rainbow-type structures, some halos, some glories. He was quite interested in how you get particular optical phenomena resulting from light traveling through moisture-laden air. In other words, air with a lot of water vapor in it. How do you get these optical phenomena? Rather than set up a laboratory on the top of Ben Nevis, he said, can I actually reproduce these in the laboratory back at sea level? Can I make clouds in a chamber to study these sorts of events? So that's what he did. He made himself the first cloud chamber back in 1911. But it wasn't too long after he set up this cloud chamber that every once in a while he noticed tracks that kept appearing in his cloud chamber. Whenever he set up clouds in order to study how light behaves, before he switched on any light, he saw these tracks coming through, which he deduced were charged particles passing through the cloud chamber. So charged particles left visible tracks. This is the first time we've been able to see subatomic particles for ourselves. And that's why it made such a huge impact in the field of experimental particle physics, because for the first time, experimental particle physicists can generate particular particles, and rather than simply theorize as to what they were doing, they could actually see what they were doing, because they could see the interaction of these things. They could apply a magnetic field and see which ways the particles bent, indicating is it negatively charged, is it positively charged. So they could do their physics using cloud chambers. And for that, he was awarded the Nobel Prize in 1927, and the citation, the most original and wonderful instrument in scientific history. That is quite a claim for any individual scientific piece of equipment, but that is just a reflection of the impact it had on the field back in the early 1900s. So that's what it looked like originally. That has morphed somewhat, because that's what it looked like in 1911. That's my version of it as of 2024. So I'm not going to say a great deal about my design of the cloud chamber, but that's what it looks like. Yes, I know if NASA was ever going to land a cafetiere on the moon, that's what it would look like, but that's just the result of having the bits that, you know, just easily accessible, buy them on Amazon, put them together, make yourself a cloud chamber. What matters is there's alcohol inside the glass jar, and there's a heater at the top, which evaporates the alcohol, and there's a little fridge unit, a little refrigeration unit, which you can buy on Amazon for a few pounds, and that takes it down to minus 25 Celsius. And because vapor is generated at the top, and because it's cold at the bottom, clouds start to form just above the cold plate. And when they just start to form, just like an aircraft flying through moisture-laden air will cause a contrail to form if it's flying at the right height, so particle tracks moving through the cloud chamber will leave a trail of alcohol droplets behind them going through. So I'm not going to talk much about the design, but I have on the table over there a set of instructions as to how you can build a cloud chamber for yourself. It'll cost about £35, depending on what bits and pieces you already have lying around. So let's see if our cloud chamber has gone back to cosmics. Let's go back to the... I'm not going to dwell on this too much, because sometimes it plays ball and sometimes it just refuses to show anything. Oh, okay, we have a new one straight away within a few seconds of switching back to cosmic rays. So let's just give it a few more seconds and see if anything else shows. There's another little one there, a little, I think that might have been an electron coming through, another couple of particles. You can see a little bit of pulsation in the background, because that's how the cloud droplets are forming. Let's just give it a few more seconds. Maybe nothing else is going to show up at this point. Generally speaking, cosmic rays turn up every second or two. There was one appearing just at the top, but it didn't produce much of a track. Another one in the center there. I think that might be all we're getting for the time being, so I think I'll just switch back to the PowerPoint. So that, again, is a video I've taken some time ago, just to give an idea in case the cloud chamber wasn't performing. That was a nice electron, another one. Oh, that was a nice proton, really bright one coming into the right-hand side there. So this is just a video I took just in case there was any problem with the cloud chamber showing cosmic rays. Again, if we take a video, in this case a much longer video, not just 1 or 2 minutes, but quite a long video, and then just add all the frames together to see what do you see if you let the cloud chamber run for an hour or so, that is the result. That's how much you might see. All the wiggly things are electron tracks. The straight ones are either muons, or if they're particularly bright and straight, they are probably protons. So there's lots of different particles in there. No alphas, because I'm only showing the cosmic rays in this particular image. I did see some alphas when I took this video, but I have not included them in this particular montage because they are not of cosmic origin. So how do we see cosmic rays? Well, we've been seeing cosmic rays for quite a while, both on the ground and in particular, now that we're in the space age, it's been possible to go above the atmosphere to find out what these primary rays actually are. How did we determine that? Well, we put cosmic ray detectors on various spacecraft, and we've been doing that for half a century or so. So Voyager 1 and Voyager 2, for instance, launched in the 1970s, now flying out of the solar system. They've got cosmic ray detectors on them. And in 2012, Voyager 1 measured a significant change in the cosmic ray flux, which told it you're now leaving the influence of the sun and you're now moving out into the solar system, out of the solar system into interstellar space. The jump in cosmic ray flux told them that they had passed the boundary, if you like, of the solar system into interstellar space. Voyager 2 was the same, but Voyager 2, because it got a deceleration as it went past Neptune, Voyager 2 is actually moving a little bit more slowly, so it wasn't until 2018 that Voyager 2 left the solar system and again saw a sudden increase in cosmic ray flux on that particular detector. There's also cosmic ray detectors sitting on the space station, a so-called AMS. AMS stands for Alpha Magnetic Spectrometer. It's basically a large, it's not a cloud chamber, it's a large solid-state electronic detector that can detect the flux of particles, and that's basically how we know that most of what's hitting the Earth is protons plus a few alphas plus a few bits and pieces of other things. It's instruments like that. But how do we detect them on the ground? Cloud chambers were great 100 years ago, but that's not how we detect cosmic rays now. One of the biggest cosmic ray observatories at the moment is the so-called Pierre Auger Observatory, which is sitting in Argentina. Again, an artist's impression says if you get a single particle coming in, it could produce thousands or many tens or hundreds of thousands of secondary particles, some of which will reach the ground. So ideally, because the shower spreads over quite a large footprint, you want to spread your detectors, I'll come to what these detectors are in just a moment, you want to spread your detectors as far and wide as possible. So if you want to put your detectors over a large area, there's a close-up of what they look like, individual tubs, if you like, individual tubs of water as it happens. What sort of area do you need to cover? Well, ideally, the largest area you can get away with, which is one of the reasons it's put into the middle of nowhere in Argentina. This particular observatory covers an area equivalent to the size of Luxembourg. That gives you an idea of how big this observatory is. So these are not cloud chambers, these little tubs. They're actually tubs of water. And what happens is any cosmic rays that goes through this tub of water produces a flash of light. Why do particles traveling through water, or indeed through air, produce a flash of light? Well, it's analogous to the idea that if you think about an object traveling through the air faster than sound, what happens? When you have an object passing through the air faster than sound, you get a shock wave. You get a sonic boom because the air can't get out of the way fast enough. Well, actually, there's an equivalent to that is not for sound, where objects are traveling faster than sound can travel through the air. What if you can travel through air faster than light can travel through the air? That's possible. Nothing can travel faster than light in a vacuum, but light is slowed down in air or slowed down in water in those tubs we saw just a moment ago. So it is possible for a particle to travel through water or through air faster than light can travel through the water or through the air. And then you get the equivalent, not a sonic boom, but a photonic boom. And this little cartoon shows what's going on for an incident particle. An incident particle produces a whole shower of secondary particles. Each of them might be moving so fast, they're moving faster than light. And they produce a photonic boom, a flash of blue light. So by the time you've got thousands of these particles, they produce a sheet of light. It's called Cherenkov radiation. It is a flash. It happens in a billionth of a second. This, of course, is slowed down considerably. And a telescope called the Cherenkov Telescope Array, with telescopes in the Atacama Desert and other telescopes in the Canary Islands, are being built to do precisely that. They are looking for the flash of light produced when a particle moves at high speed through the Earth's atmosphere. So they're looking for the blue flash in the sky. What we saw before with the Pierre Auger Observatory, they're looking for the blue flash through each of these tubs of water. Same principle, different medium. So in the case of the Cherenkov Telescope Array, there's loads of telescopes being built looking at the sky. Hopefully the sky is nice and dark and you can pick up this blue flash, and that tells you that a very energetic particle has passed through the Earth's atmosphere. A whole load in the northern hemisphere on the Canary Islands, a whole load in the southern hemisphere in the Atacama Desert. But you're not restricted to only looking for particles traveling through the air or particles traveling through a tub of water. You could use water in a different form if you wish, and that's what they've done at the South Pole. You already have a whole load of water there. Well, actually it's ice, but it doesn't really matter. Cherenkov radiation doesn't care that it's ice rather than water. So below the Antarctic ice cap, there's the bedrock, and we've got more than a kilometer of ice. What they've done is put a whole load of photodetectors in a cube of ice, 1 kilometer by 1 kilometer by 1 kilometer. In other words, it's an ice cube, literally 1 cubic kilometer in size. If you're struggling with the scale, there's the Empire State Building to give you an idea of how big this is. So they have thousands of photodetectors looking for the blue flash. And what happens is, if a particle comes through the Antarctic ice cap, through this particular kilometer cube of ice, it produces a blue flash, and some of those photodetectors record that blue flash. And if you look at which photodetectors fire, you can effectively say that particle came from that direction by looking at the geometry of where you see the blue flash. And that comes to the final section. Okay, right, we now have the detectors, we have the technology, so we should be able to tell where these things are coming from. If these protons or nuclei of alpha particles or nuclei of helium, otherwise known as alpha particles, or heavier elements are coming from, where are they coming from? What is the source of these energetic particles, these charged particles? Why are they flying around the universe and hitting our atmosphere? Just as a little bit of an aside, do you realize it's just over 100 years since Hubble said, if we look at these spiral nebula that we see, it looks like they are not nebulae inside our own galaxy. They are galaxies in their own right at distances of millions of light years. So a few months over 100 years. It was November 100 years ago last year that Hubble said, we have now put this debate to rest. The universe is not just our galaxy. The universe is trillions of galaxies beyond our own. So in terms of how that relates to our cosmic story, we know that cosmic rays on the whole don't come from the sun, but if they come from beyond the sun, the argument, I should say the question is now, if they don't come from the sun, do they come from our own galaxy, or apparently the universe is now full of other galaxies, so do they come from our galaxy, or do they come from other galaxies elsewhere? Are they galactic, or are they intergalactic in origin? So can we tell? Shouldn't that be easy? Well, not necessarily. Do we know what accelerates particles to very high energy? Well, it is thought by theorists, surely it's going to be shock waves that generate the sort of energies we need to explain high energy particles hitting the Earth. Either supernova, which we know generates shock waves, or we also have seen evidence that jets of supermassive black holes generate shock waves as well. So if shock waves perhaps are responsible, we don't really understand the mechanism. Some theorists say, well, it might be possible for particles to get accelerated and re-accelerated and accelerated again by continuously going through the boundary of a shock wave, but understanding the precise mechanics of how that works is still a matter for debate at the moment. So maybe shock waves of supernova or shock waves from black holes can actually produce the sort of energies we're talking about. But to pin down, well, is it can we tell if this supernova has generated any? Can we look at cosmic ray events and work out, did they come from this supernova remnant? Did they come from that galaxy, which has got a very active nucleus? Can't we just trace back which way they came from and work it out? If we've got a particular shower and we know which direction that shower came in, because our photodetectors can effectively tell us the direction of the incoming particle, can't we just trace them back and say, well, it's that object there that's producing all these cosmic rays? It should in principle be simple, but it's complicated by the fact that, unfortunately, charged particles can be affected by magnetic fields. And magnetic fields are pretty much everywhere. So we know, for instance, the Earth is surrounded by a magnetic field, and low energy stuff, the relatively low energy stuff from the sun, particles get trapped in the Earth's magnetic field and funneled towards the north and south poles where we see the aurora. More energetic particles won't care about that magnetic field, but there may be other magnetic fields out there. So we can see the magnetic field of a bar magnet just by looking at iron filings. That's easy. But how do we see magnetic fields that are cosmic? Well, it turns out that we can actually see some of the magnetic fields within the Milky Way, because dust particles tend to get aligned by magnetic fields. So if we see which way the dust is sitting, which we can do by looking at polarized light, we get an idea of what the magnetic field of the Milky Way looks like. And that has been done by the Planck satellite, for instance. But it's nowhere near as neat as the dipole magnetic field of the Earth. It is a very complicated structure trying to work out what's going on. And have we got any chance of understanding what the magnetic field outside our galaxy is? How on earth can we map out what the magnetic field lines are like from one galaxy to the next? If we're trying to work out where particles are coming from, and if particles are affected by magnetic fields, if we don't understand the magnetic fields, then the paths of these particles are going to get scrambled, and we've got no idea where they're coming from. The only saving grace is that we think the most energetic particles will be least affected by magnetic fields. So although we don't know necessarily where the magnetic fields are and how they're oriented, if we concentrate on only those most energetic cosmic rays, hopefully they'll cut through the magnetic fields and hardly be deflected at all, and hence we will be able to point to the smoking gun of which object has produced all of these cosmic rays. So we need to think about the energy of cosmic rays. This is a scale that physicists use, the energy of particular particles. For instance, the photons that are currently hitting my hand from the projector, visible light photons, have an energy of 1 eV. We're not going to worry about what that unit is. Let's just take eV as the unit of visible light energies. If we go 1,000 times more energetic, we get to X-rays, which of course can penetrate much more than visible light can. If we go to 1,000,000 times an eV, we get to the energies of alpha and beta and gamma particles spat out from radioactive samples. But for cosmic rays, we have to go to 1 billion or 1 trillion or 1 quadrillion or septillion. We have to go way, way, way higher than these sorts of energies. Some cosmic rays are exceptionally energetic. Some of the low end probably come from the sun, but probably some of the high end, where on earth are they coming from? So just to give it some context, the energy that we can generate in the Large Hadron Collider is about where that left arrow is. And if we ever build something bigger than the Large Hadron Collider, that will give us energies roughly where the right-hand arrow is. So some of these cosmic rays are hitting Earth with energies far, far, far higher than anything we can possibly generate with even the most powerful particle accelerators on Earth. We think the number that are hitting looks something like that. The ones on the left, the yellowish color, they are probably coming from the sun. The middling energies come from somewhere in the galaxy, we think, but we're not sure. Some of the most energetic cosmic rays we think are coming from outside the galaxy. But this is, at the moment, conjecture. But what we do sort of know is that the number of particles falls off very steeply with energy. We get lots of the low energy things, we get very few of the high energy. And in terms of numbers we can understand, at the very low energy end, we might get 1 particle hitting every square meter of the Earth's atmosphere every second. For the middling sorts of energies, we might get 1 hitting every square meter per year. At the very high energy end, we might only get 1 per square kilometre per year. So if we want to see any of the showers produced by these particles, we have to have either very big detectors or we have to be very patient because we're not going to see them coming along very often. So we really want to catch these ultra-high energy cosmic rays, not very common, but the ultra-high energy ones hopefully will not be deflected by magnetic fields, and so we can tell where they came from. So we can pin down the source of these enigmatic cosmic rays. So a little while ago was the Amaterasu event, or Amaterasu event. This was picked up by a telescope array in the USA. It was reported in Astronomy Picture of the Day at the end of 2023. It was referring to data that was picked up in 2021. It was the second most energetic thing that we ever detected hit the atmosphere of the Earth, the second most energetic particle. And the Amaterasu particle should not be confused with the tiramisu particle. That's a completely different thing. But this one, a very energetic particle, we figured that this one is probably energetic enough to tell us what we need to know. So the entire array of detectors here, some of them lit up, and it allowed you to backtrack and work out the geometry and the energy, because the energy of everything that hits here plus everything we miss, add that all up, that gives you the energy of the incoming particle. That was then backtracked to see where it came from. So we're hoping that this is a high enough energy that we can do that. So what happened? They worked out the geometry of the Amaterasu event, and they said, right, let's work out the geometry, and we know the timing. So they pointed back along this line, and what they found was it points to, pause for dramatic effect, it points to nothing. No supernova remnant could be found in that direction. No galaxy with a supermassive black hole or very active galactic nucleus could be identified. So although something extremely energetic hit the Earth, we assume it came from that direction, but there doesn't seem to be anything in that direction. Does that mean we've got the physics wrong? Does it mean the magnetic fields are stronger than we thought and it actually got bent and it actually came from over there, not over there, and we're getting all our directions wrong? Or does it simply mean we need to take more data? We need more observations, we need more showers to appear so we can get this backtrack sorted out to actually figure out what is it in the sky that's producing these energetic particles. Dark energy is not a mechanism to accelerate particles, no. Just how close to the speed of light are these things going? For a physicist, if something is very energetic, that means it's traveling very fast. It's exactly the same thing as saying if it's traveling very fast, it's got an awful lot of energy. So one way of equating just how energetic are these particles is to ask, well, how close to the speed of light are they traveling? We know they can't travel faster than light because they're massive particles, they're protons or alpha particles. But we can calculate just how fast these things are traveling. So if we take not the Amaterasu event, which was the second most energetic particle, if we take the most energetic thing that's ever been seen hitting the Earth, that one was called the oh my God particle because when it was seen, scientists could not actually believe that any individual particle could possibly have that much energy. But it appears to be a genuine observation. No one has proved it wrong. But when you work out not the energy of the particle, but if you convert the energy of the particle to how fast must it have been traveling, if it was a proton, for instance, which is the most likely source and most likely particle, then you can calculate as a percentage of the speed of light how fast was it going. And the answer is 99.9999, not done, 999, still not done, 999, 999, still not done yet, 999, 999, okay, nearly there, 995% of the speed of light. How on earth did anything get that fast? What mechanism can possibly accelerate a particle that close to the speed of light. That is still a mystery. And of course, it's impossible to visualize, apart from counting how many nines there are in there, it's impossible to visualize just how close to the speed of light that is. So some way of putting a little bit of perspective on that is to say, hypothetically, let's imagine that in a perfect vacuum, we had a race between this most energetic cosmic ray that we're talking about and a photon of light. Let's imagine a 100,000 light-year racetrack sitting there in a perfect vacuum. We are going to start this cosmic ray and a photon of light at exactly the same time, and they are going to race 100,000 light years. Now, we know the light is going to win. The light is going to win because nothing can travel faster than light in a perfect vacuum. But the question is, when the light crosses the line, how far behind it is the cosmic ray after 100,000 light years? The answer is 5 millimeters. Having traveled across the diameter of the galaxy equivalent, it's only lost 5 millimeters in the entire race. If you want to convert that to time, if you start a stopwatch when light crosses the boundary and then stop the stopwatch when the cosmic ray crosses the finish line, what's the time difference between them after 100,000 years? The answer is about a nanosecond. So these things are flying through the universe incredibly close to the speed of light, having been accelerated by a mechanism that we really don't understand, and we don't even know where that mechanism is operating. Is it supernova? Is it black holes? Is it something else? So let me just summarize. Cosmic rays, they are accelerated somewhere, somehow. We have ideas, but we don't really know. Probably supernova, supermassive black holes are sources, but we can't actually pin that down because we can't pin back the direction of a particular shower to a particular source. Supernova and massive black holes, probably, maybe we're missing something else. Maybe something else is accelerating them, which is why when we look in that direction, we can't see any obvious candidates. Cosmic rays are charged particles, so they're deflected by magnetic fields. Lower energy particles will have their paths completely scrambled by all of the magnetic fields in the solar system, in the galaxy, in between the galaxies. They will scramble any attempt to work out where they're coming from. We hope that the really high energy cosmic rays will have their deflections small enough that we have a chance of working out where they actually came from. Some particles make it past the Earth's protective magnetic field, especially at the low end. Some particles are protected by the Earth at the low end, but some particles make it past the Earth's magnetic field, especially the high energy particles. And whenever something hits the atmosphere, we get an air shower of secondary particles. Some of the secondary particles will make it to sea level, some might not, but quite a few do, including muons, electrons, protons, and probably a few others. And they result in clicks in a Geiger counter and tracks in a cloud chamber. So when we look in a cloud chamber, we see all sorts of things flying through. And when we listen to a Geiger counter well away from a radioactive sample, we hear the occasional click. Remember, these are particles that may have started their journey in a supernova in our galaxy, or possibly in the jets of a supermassive black hole in an entirely different galaxy a long time ago, far, far away. So in a sense, when you listen to those clicks, you're listening to the cosmos. Thank you.